All right, today we're going to be looking at section 2.5, limits at infinity. In this section, we're going to be looking at the end behavior of graphs as x gets infinitely large or infinitely large in magnitude in negative direction. So one of the things that causes an infinite limit to approach a finite number would be horizontal asymptotes. And so this kind of goes over some of those properties in some of the graphs that you'll see. And then we get down to the first definition, and you usually get a visual that kind of helps you understand it. So you have limits at infinity and horizontal asymptotes. It says if f of x becomes arbitrarily close to a finite number L, so that's saying your y value is getting close to a point, maybe it's flattening out on the end as we go further and further to the right, for all sufficiently large positive x. So that again, so as x is going to infinity, the y is getting close to some L value. Then we write limit of f of x as x goes to infinity is equal to L. And then it tells you how to say it, and then it shows you that y equals L is a horizontal asymptote of the graph f, and then it shows you figure 2.3. So, and the same can be said for negative infinity. And they just use the letter m to denote a different y value. Then we get a few graphs to kind of see how to evaluate. So they're just showing you when you have graphs going toward infinity, you can kind of think about what's happening as x gets really big. This overall fraction is going to 0. And remember, we talked about the sum of limits is the limit of the sums. And so you can split this up and get two separate limits and find the limit here, which would just be 2. And then the limit here goes to 0, so they just show you that it equals 2. So these are good examples to kind of look at, read through, and kind of understand what's going on. So then we have the second scenario. If f of x becomes large as x gets large, then we write the limit of f of x as x goes to infinity is equal to infinity. So this time it's not approaching a number, it's just increasing and increasing without bound. Same can be said for the negative side. So again, they just kind of go over each part. If you go to positive and it goes to negative, it might go to negative and you go to positive infinity, and if it goes from negative to negative. So you got all the different scenarios. Here are some graphs. Mainly you want to look at the largest degree. The degree will give you an indication if both endpoints go up to positive or down to negative. And then when you have an odd degree, usually one side goes to positive infinity and the other goes to negative infinity. Theorem 2.6 goes over limits at infinity of powers and polynomials. So you have some polynomial, these properties will hold. If you have x to the n, as x goes to positive or negative infinity, it will go to positive infinity when n is even. And this is if you have a positive coefficient. If x goes to infinity, xn goes to positive infinity, and the limit goes to negative infinity as xn goes to negative infinity, this will happen when n is odd. So when it's even, they both go positive. When it's odd, positive to positive and negative to negative. Rational function, polynomial is the same as x to the negative n. This will go to 0. You'll have an asymptote. And then just a general statement, as x goes to positive or negative infinity, the polynomial will go either to positive or negative depending on the degree of the polynomial and the leading coefficient. And then you got some examples that kind of show you and walk you through what's going on. Again, thinking about as x gets really big, they kind of ignore all the other ones because this is the biggest one, and so this one is going to have the most pull, this one is going to affect the graph the most, and so you focus on the largest exponent or the largest degree. We kind of review over end behavior. This is something you might have seen in algebra. Whenever you have rational functions, we got to determine what's going on at the end of the graph. And then here's a certain approach. You look at the largest degree in your denominator and you divide everything by that degree. And then you look at what happens as x gets really, really big. Usually if you have a finite number or smaller number over a really large number, the fraction is going towards 0. So the top is going to 0. They do the same thing with the bottom. You end up with 1, 0 divided by 1, you get 0. So this is going to be the method to solve these. Again, they give you some examples and some graphics and images. They want to remind you of how to find asymptotes. You've got to look at the degree of the numerator compared to the denominator. There's 3 different scenarios, and then there's a 4th when you have a slant asymptote. And those are described here. So when we're looking at end behavior, says suppose f of x is equal to p of x over q of x, where we have a rational function, and it's telling you the rational functions of this form. The degree of the numerator, if it's less than the degree of the denominator, so the degree of the top is smaller than the bottom, then you will have a horizontal asymptote of y equals 0. If the degree of the numerator equals the denominator, so the top and the bottom are equal, then your horizontal asymptote will be the line y equals a over b, where a and b are the coefficients of the numerator and denominator respectively. And then C, if the degree of the numerator is greater than the denominator, then your graph has no horizontal asymptote. So these are the 3 scenarios you might remember from algebra. And then we talk about slant asymptote. So if you have a slant asymptote, the degree m is going to be equal to n plus 1. So the degree in the numerator is going to be exactly 1 more than the denominator. So if you notice the top is exactly 1 more than the bottom, then you will have a slant asymptote, and you will find that by doing synthetic division or long division and finding the linear factor. It should be in the form y equals mx plus b. Looks like a line, but they don't give that much information here. And then if you have vertical asymptote, you just find what makes the denominator 0. So whatever causes the denominator to equal 0, those will be vertical asymptotes, provided that they don't get divided out or canceled out when you factor. So here's another one with end behavior, algebraic reasoning. If you have square roots, you got to remember how to evaluate square roots. Remember, the process is going to be divide everything by the largest degree that you have in your denominator. And what they show you over here is that the square root of x to the 6 is the same as x to the 3rd whenever you reduce the radical. So the largest degree in the bottom is x to the 3rd, and that matches the top. So when you pull that term out of the square root, you're dividing by x to the 3rd, and then in the square root is x to the 6th. And they do the same thing. They look at what happens as x goes to infinity with each term and simplifying, and we can find the limit that way. In addition, we look at some transcendental functions. So we have e to the x, natural log. They talk about the end behavior of those. These are some common graphs that you want to be familiar with from our parent functions. And then we talk about the same thing with some trig functions. So it's transcendental functions. And so you kind of see some with cosine, sine, and we'll play with those as well. Okay, so that's the general overview. With that, I'll jump into my math lab and we'll do a few examples.